Hello. We'll do some calculus today. Applications of what we learned in the first three courses. So all these things are really useful for problems in analysis and probability, and there will be a lot of computations. So very interesting stuff today. Let's find this presentation. So here we go. Linear algebra and calculus questions. So. Uh, Well, of course, linear algebra, any kind of algebra is more for solving questions, and the real problem is to do analysis, right? So that's what we learn today, learn applications, all these things like see how matrices appear in analysis and why is it useful to diagonalize them and applications, all this. So let's start with something very simple as an application like systems. Well, this is still algebra. So any system of linear equations, you see just a system like this, some variables, x1, xn, coefficients. Well, this can be solved very easily with matrices. So this in matrix form means just that I have the matrix of coefficients multiplied by this column vector of variables, and that should be the output here on the right. So this is simply ax is v, right? So if a is invertible, the solution is simply x is a minus 1v. If a is not invertible, it's a bit more complicated, but can be solved with linear algebra. So that's it. I mean, given any system of linear equations, the problem is to invert the matrix. That's it. Now, another application, let's look at recurrences now. So this is something that you probably know. And it's quite tricky. I mean, if you have several, you see a general recurrent system like this with the unknowns being the x's and y's and z's and maybe some more. So I don't know where to start with the alphabet here. That's why I put these dots. And this sequence is, you want to compute them at the same time. And at order k plus 1, each of them is a linear combination of guys at order k. Okay, that's what happens for x. Xk plus 1 is something like this. Yk plus 1 is also a linear combination of the guys before, and so on. So to solve it, it's again, as for systems, I mean, what we have here is a matrix multiplication. So in matrix form, you see I put the unknowns here at level k plus 1. And this is the matrix here of coefficients multiplied by things at level k. So if we think a bit, well, that was exactly as for the systems, but now instead of computing a minus 1, we are in of computing the powers, ak. Why? Because what happens here is that every time when going from level k to level k plus 1, I multiply by a. Okay, so for getting to level k, starting from the data from level 0, you have to multiply k times by the matrix A. So finally, the solution is obtained by applying a to the k to the initial data. So end of the story. I mean, this problem also belongs to linear algebra, and the problem is to compute the powers, aka. Now, these powers are quite tricky to compute. Even if I give you a 2x2 matrix, it's going to be hard if you try to compute the second, third, fourth, fifth power to guess the formula. Typically, you won't guess it. I mean, it becomes very complicated. So the point is that you have to diagonalize the matrix, so PDP minus 1. And then once the matrix is like this, the powers are just PDKP minus 1. So why? Because, well, either you can see it from the formula. I mean, you put PDP minus 1, PDP minus 1, and so on. And all the PP minus 1s in the middle will simplify. So you're left with the first P, the last P minus 1, and then the diagonal matrix to the K. Or you can read directly. I mean, diagonalization means that in a certain basis it multiplies by lambda 1 in this direction, lambda 2, lambda 3, and so on. Now if I apply k times the transformation, once again in this new basis, this multiplies by lambda 1 to the k, lambda 2 to the k, and so on. So it's exactly the formula written over here. So that's the thing well, in practice, I mean, d to the k is clear, right? You just raise the eigenvalues to the power k, and then you have to multiply by pp minus 1. And the answer is a linear combination of powers of eigenvalues. That's why I cannot guess it. So these things can be really tricky. So that's the way to solve them, and the only way actually to solve them in linear algebra. If you have at least two or maybe three variables here, yeah, there's no other way. So now this formula, just as a remark here, so well, this is true for k integer, but it's also true for negatives, right? If you want to invert the matrix, that's going to be pd minus 1, pdp minus 1, and then you can take negative powers. And well, it's actually true for pretty much every function. I mean, it's also true for powers, real powers. Also, you can put exponentials, whatever other functions. So just thinking a function, well, a suitable function of the matrix, like in Taylor series, is P, then the function of the diagonal matrix, and P minus 1. We'll be back to this kind of things when doing analysis. Okay, now calculus. Yeah, let's review a bit the basic calculus. So what we know, yeah, derivatives, integrals. So where is linear algebra good in all this? That is good in when you do it in several dimensions. Okay, so let's start with the basics. So yeah, that's your derivative. Okay, so this means exactly that any function can be approximated by in this way. So f of x plus t small is f of x. And the fluctuation there is linear. I mean, it's a being the derivative, right? At order 1. Now, if you want to get to n dimensions, well, it's going to be more complicated because you have several variables there, and well, let me show the formula. So once again, the formula is the same as before, but now we have a vector variable here, which is small. And well, you have to apply to it a matrix, which is the matrix of partial derivatives at x. Okay, so it's exactly the same formula as before. Let's go back. F of x plus t is f of x plus at. That's what was written here, except that a was just a derivative, it was a number here. So t is a number, I have to multiply by a number. Here t is a vector, I have to multiply by a matrix in order to get the vector. And why do we get the derivative? Because well, I mean, let's say, well, if this thing, for instance, is diagonal, it's clear that you have to multiply in each direction with that quantity. So yeah, in general, it's not it's quite clear from the you can get it from this. Okay. So this was about derivatives. Now let's get to integrals. So once again, start with one dimension. Remember, we have this change of variable formula that you know very well. So that's the formula. Well, for us from this rule of differentiation. And actually, the best way to remember this is, first of all, the bonds here. If you put the bonds here, you should put them below because the formula becomes complicated. So these are the bonds which make the formula work. I mean, if you plug in when t varies from here to here, phi of t varies from a to b. So the bonds must be this and this. And in order to remember this, the idea is that if you let x to be phi of t, then dx, so we put phi of t here, okay? And dx will change. dx is d phi of t, and d phi of t is phi prime of t dt, okay? That's the way of remembering it. Now, what happens in n dimensions? Well, once again, we have vectors and everything. So the transformation now phi will have n components, each of them being a function of n variables. And the formula is exactly as before. So f of phi of t, and here I must put some kind of derivative. Which derivative? It's a so-called Jacobian. So I take the matrix of partial derivatives, and then I take the determinant. Okay, so I need a number here. It's not like for what we're doing before. Let's go back before. You see here I have this matrix multiplied by a vector. Now here I don't need a matrix, I need a number, and the number is the determinant of that guy. So of course this generalizes what happens in one dimension. Now why is this true? And why the determinant? I mean, the determinant is complicated business, right? And the thing is that it's not. I mean, if you remember the definition of the determinant, it's just the volume of these vectors, right? The volume, that's all. So for a linear map, the determinant, the associated matrix is somehow the inflation coefficient of the map. I mean, the linear map will send a unit cube, something like this, a kind of parallelogram, and you measure the volume of the parallelogram, and that's the inflation. I mean, the unit cube having volume 1 will get inflated, okay? So that's the determinant, it's this inflation coefficient. Now, if you think of it a bit, what you need to put here, the number is the inflation coefficient of phi. Now, phi being somehow linear at first order, it's just this matrix, and then the inflation coefficient is that. So there are two things here. Anything is linear at first order. That's the principle here with derivative, these kind of things. More precisely, this thing here. So that's the first principle. Phi, somehow, in order to do this kind of thing, you have to linearize phi. That's your phi. Okay, first order. The second thing is that the number here is the volume. It's not all the phi itself which matters, but just the inflation coefficient. And that's the one. So all this is, yeah, of course, it's tricky. So usually people skip the proof of this, and then the complete proof is complicated. These things. Now let's look for some applications of all this. Polar coordinates, yeah, that's the simplest change of variables, which is extremely useful. So r cos t, r sin t, of course, right? And we'll take points in the plane. That's your r, that's your t, r cos t, r sin t. So in order to apply the result, you need to compute the Jacobian. So if you take the derivatives of these guys with respect to r and then to t, you get this matrix was the determinant r cos square plus r sin square, so it's r, okay? So that's the thing to know. The polar coordinate is the obvious thing, like a windshield wiper, right? That's your t and the r. And the only thing to remember is that the Jacobian is r. Forget it, that's a computation. Get it in 5 seconds. Well, application of this. So what's this integral? This is a very tough integral. You won't get it. I mean, you can use all kinds of methods to change your variables, everything. You won't get anything. So there is a trick. This is the so-called Gauss integral, and here's the trick: is to compute the square of this integral, because the square, you can see I can write it like this with 2 variables. It takes place in R2, and in R2 I can use polar coordinates. In polar coordinates, it gets extremely simple. You see, I have no t here. And this function of r, what matters is the distance r. This function is the derivative of something, so we're done, okay? And you get I squared is pi, so I square root of pi. So this is very important in mathematics, because as an application, you can define the normal laws or Gaussian laws. So here's your normal law, and more generally the normal law of parameter t, you can define it like this. These are centered, okay? I'm doing probability now. And the Gauss formula tells you that these are indeed probability measurements, and they are mass 1. If I integrate this density, I get 1. Okay, so the square root of pi here is the square root of pi here, okay? There's a factor 2 because it's a customary probability to divide by 2 here, okay? Well, let's not get into all this for having variance 1. And okay, so same for Gaussian law of parameter t. I mean, everything comes from this Gauss formula. We need this thing here. I mean, the formula in order to guess the coefficients. So this you can do probability theory. So it is quite fun. I mean, probability theory actually needs linear algebra in order to get started, right? So for doing probability, you need the Gaussian law. For Gaussian law, you need the Gaussian integral. For Gaussian integral, you need polar coordinates, and for polar coordinates, you need linear algebra, the Jacobian. Quite nice. Now, let's talk also about spherical coordinates now. So it's 3 dimensions. Well, you have to think a bit, but you see in 2 dimensions, it's like this windshield wiper principle, right? That's your t and then r. Now, if you have the sphere, well, you have 2 angles, right? You have to wipe in all 2 possible directions somehow. So that's your formula: r cos s, r sin s cos t, r sin s sin t. How to remember this? well, it's somehow intuitive. So I start, let's go back to the polar thing here, r cos t, okay, r sin t. So start to r cos's, and then you have to add somehow one more angle. And then, well, the sum of squares must be r squared. So if you sum this plus this square, things will simplify here to Pythagoras cos square plus sin square is 1, and then again. So it's somehow the only possible formula which such that the sum of squares is 1. That's how to remember it. And the Jacobian now is computed. So yeah, it's a 3 by 3 determinant to do the computation and get r squared sin s. Okay. Now, let's do it in n dimensions now. So same principle as before. I put an angle, cos, and then sin, add a cos, and so on, so on. And the last thing is only sinuses. And you see the angles are, I don't need n of them, I need n minus 1, okay? It's like in 3 dimensions, I need 2 angles and so on. It's 1 and minus 1 angles. And the Jacobian is this guy here. And well, if you ever forget, well, this thing in 3 dimensions, you can get it in a few minutes. In 2 dimensions, it's obvious. So somehow this formula comes by thinking what comes next, okay? So it's all the sinuses with powers. Good, so now let's see an application of this. So yeah, what's the volume of the sphere? So you probably know it in 1 to 3 dimensions, but not in 4. Here's your formula. So there are many possible formulas, and that's my favorite one. I mean, it's really very compact, and it works for n odd and even. So v over 2n. Why over 2n? Because it's somehow the positive part. You see, if you take the sphere in 2 dimensions, I mean the disk, that's the quarter of the disk, which is positive. In 3 dimensions, you have 1/8 of where the coordinates are positive. So it's somehow the positive part of the sphere, okay? So it's pi over 2 power integer part over n over 2, and then 1 over double factorial with this convention for the double factorial. It's product n minus 1, n minus 3, and so on, stopping at 1 and 2. So if you see particular cases, in 1 dimension you get 2, which is correct. I mean, the sphere is the interval minus 1, 1. The volume is the length, so length 2, okay? In 2 dimensions, yeah, what's the area of the disk? Pi. In 3 dimension, 4 pi over 3. And now in 4 dimension computation, so let's go here, v over 16, we get pi over 2 squared, so pi squared over 4. And this factorial guy, so let's plug in n4. This means I have to take 4 times 2, and it stops at 2. So it's 8. So pi squared over 2. That's the formula. So very, very nice. I mean, that's a formula. If you look everywhere, like Wikipedia, whatever, you find a lot of formulas which are very bad. And that's the good formula. The positive part is this very simple thing. It's really very uniform. So to prove this, well, of course, you just have to take spherical coordinates and integrate all that guys there. So let's go back here. You have to integrate something like this. So finally, by Fubini, you're left with just have to compute integrals over the circle. Powers of cos and powers of sin, that's what you need. And you probably know a bit how this works. I mean, you probably know it for PQ is 1 to 3. Here's your general formula with that convention for the factorials that we used before. So it's a power of 2 over pi, and then these double factorials. So you get this with the partial integration, a double recurrence. If you do a partial integration, you'll get the double recurrence, you solve it to get these factorials. So with this, you can compute everything. I mean, not only the volume of the sphere, but the integral over the sphere. Exercise, let's say, and exercise. So yeah, that's a very good formula. Okay, so that was it. Hope I had fun. Yeah, a lot of calculus and linear algebra is important. Okay, it's needed for everything. See you soon.